Okey-dokey. So, on Monday, I guess we were going through some of these remainder mechanisms, I guess, or reactions that we had in the carbonyl and ketone chapter here, and we went through and looked at the Wolff-Kishner reduction. We learned about the Schiff-base reaction. Then we learned about imine formation, right? We talked about imine and imine. We'll try this here, right? Imines and enamines, and we talked about how we would get back to the idea of enamines in one of the upcoming chapters after the exam there. How we can use those to start to build bigger molecules based off of those. But the Schiff-base reaction there, that imine formation is something that's useful for setting up a future reaction is what it is. All right, so we talked about that kind of stuff, and we have, I think only 2 more reactions that we're really going to talk about in I guess this is chapter 19, yeah, so chapter 19 here, and then that should be all we need to kind of go over, at least in this. And then we'll keep talking more about carbonyls. And then after we talk about carbonyls, we're going to talk about some more carbonyls. And then we'll finally stop talking about carbonyls for about 3 seconds, and we'll talk about amines, and then back to talking about carbonyls. We've still got quite a bit to go, but like I said, we're kind of hanging around the ketone and aldehyde chapter here for a little bit, and then we'll move a little bit to some of the other types of carbonyl functional groups that are available, right? So anyway, we need to learn about one reaction that's extremely useful, and then one reaction that has its utility at the right time, at the right place, at the right situation, at the right phase of the moon, right, on the right day of the week. No, I'm just kidding. I don't want to oversell it, right? It has its application at certain points in time, is what it is. So it's a kind of a specific reaction. But we'll mention that in just a second. So anyway, one of the ideas, or one of the let's say secondary themes of the second semester of organic chemistry is how we can start to make, let's say, larger, more complex molecules. And what I mean with that is related to one of the principal ideas, at least the way I look at it, is functional group tolerance, right, and functional group specificity. So if you think about it, right, if we have these kind of complex pharmaceutical compounds, right, they've got amines, they've got alcohols, they've got ketones, they've got aldehydes, they've got all these different functional groups in one thing, and then I need to affect a single transformation on one of those functional groups. So it gets challenging when we're like, okay, I don't want to react the alcohol, but I want to react the carbonyl, but I don't want to react this amine, and I got, right, so there's all these different functional groups in there that we have to kind of pay attention to. So one of the synthetic strategies is, instead of just building the molecule piece by piece by piece, is we find a way to join together 2 larger molecules, usually through some kind of carbon-carbon bond or some kind of other bond of that nature, right? And so to walk away from that maybe too complex of an idea there, just to think about in your head, making carbon-carbon bonds is really important. That's all I'm trying to say. We can use it to draw together 2 independent molecules, right, and link them together through a carbon-carbon bond, which is kind of the nature of all of organic chemistry, right? The nature, the chemistry of carbon. And so one of the reactions that we're going to learn about today is very useful, and it comes from, or we can start from carbonyl groups, ketones and aldehydes with it. So it's the Wittig reaction is what it is, okay? So I forget what section is this. So section, don't have its own section. What sucks? What's wrong with this? Okay, I'm just kidding. So anyway, we're on page 877 is what it is, right? So the Wittig reaction. Okay, so I guess questions for you first then. So let's talk about, let me back up for just a second. Well, you guys aren't impressed? many times have we talked about phosphorus so far? No. Not really? Was it once? Twice? Oh, okay. I don't know. You guys probably remember better than I do. I was hoping you guys gave me an answer. Right? We did have a couple of instances for this. Remember, we can use certain triphenylphosphines, PCl3, PBr3, can be used to transform an alcohol selectively into a halogen, right? Without the use of an acid, right? So we have seen it kind of pop its head up here and there, right? So phosphorus is where on the periodic table? It's under nitrogen. Okay, so what do we know about nitrogen? We've seen that quite a bit more. What are some of the important properties of nitrogen? Got lone pair. Okay, they got a lone pair and that's it. Good. All right, so what do we know? Yeah.
Do a lot of chemistry, especially like those cyano reactions.
What do you mean?
Like the nitrogen can be bound to a carbon and it can do chemistry. They're basic.
They're basic.
So one of the most electronegative.
Third most electronegative atom. That's pretty important, right? What goes along with basic and what Sophia's trying to... I know what you're trying to say. You're walking in a large perimeter around the bush there, but I got it. So we learned about cyanohydrin formation, right, with carbonyls. Right? How did that work? Well, right, they remember if something can act like a base, then they can also probably act like a... Right? So if that's all true about nitrogen, what can we say about phosphorus? Probably about the same, except it's not nearly as electronegative, which makes it less basic, but it actually is a better nucleophile, right? It's a really, really good nucleophile. One of the most common phosphorysases that we see in chemistry is this guy here, which I apparently cannot draw today, and that is our buddy triphenylphosphine. Okay? So much like an amine, right? Here we have a phosphine. So triphenylphosphine. You name a branch of chemistry, triphenylphosphine is important in it. One of the most important aspects to it is, I believe it's, well, I don't want to say something dumb now because I'm getting recorded, and I don't want the 3 people who watch this to think I'm an idiot, right? So, I'm pretty sure, if I don't know why I didn't look this up beforehand. I'm almost 100% certain this is part of the catalyst that's used as part of the Monsanto process. And you're like, wow, the Monsanto process, geez, I was talking about that before I got in here. No, so it's just one of these quintessential reactions that you learn when you become an inorganic chemist. But the problem is I learned it decades ago and I haven't taught inorganic class. I was supposed to do it here and then suddenly the major disappeared, right? But anyway, it's just one of the, triphenylphosphine is used in a lot of different places in chemistry is what it is. It's a very good ligand for metals, so whenever we're doing catalysis applications and things like that, we see a lot of phosphorus and a lot of different groups bound to it, right? Triphenylphosphine just happens to be one of these very common ones, so it's cheap, it's in every organic lab. There's actually quite a few lab experiments for, the teaching labs that involve triphenylphosphine, but I don't know about you guys. I don't think we can do that stuff. It's like next week we're going to heat water. Dr. H, mine froze. I don't know. You gotta start over. Anyway, I'm joking. But anyway, so triphenylphosphine is just again one of these very common things that we see over and over and over again. And it is one of the key reagents that's to set up a Vitic. Now to do a vidig, we have to kind of bring together two separate pieces here, right? And this kind of relates back to what I was trying to tell you guys about at the start of this whole spiel. So let's think about this. Oh yeah, sorry, one more thing. So, because nobody wants to keep drawing this, if you ever see PPH3, right? So remember, capital P lowercase h is just an abbreviation for phenyl, right? A benzene ring, right? Directly bound to something. So if you see PPH3, that's triphenylphosphine, okay? Okay. So, here's what we take. Let's take our triphenylphosphine, okay? And put that together. Okay? And what's going to happen? Give the full product. I don't know, he hasn't gotten it right yet either. So.
Exactly.
Right.
Here we go.
I'm not saying you're far off, but you guys are missing something very important, or being very cavalier.
Well, Cavalier is the king of its class. Huh? I need some of that. I'm dealing with this.
Remember, we haven't done much with phosphorus, right? We have to make a lot of assumptions that when we make bonds with phosphorus, it ends up staying neutral, huh?
Oh. You hurt my eyes.
There you go. No, that's all. Great. So if that's positive, what's the negative? Right, there always has to be a negative somewhere.
Oh, sheesh. Good job, son.
There you go. Okay, so there's a positive, where's the negative then? I'll give you a hint, draw the mechanism of how you got there,
Okay.
right?
Don't even.
So what did we say about phosphorus? I think the first thing that was said is that it has lone pair. Right? But to draw back to the ideas that we had here, they're fantastic nucleophiles, okay? Phosphorus, especially triphenylphosphine, is a really, really, really good nucleophile. Why is that important?
I can attack things.
Yeah?
And I can kick off things. SN2.
So, if you have a really good nucleophile, you have a tendency towards certain mechanisms. For instance,
SN2.
right? But to do a good SN2, what do you need? We need a leaving group, right? That is
Great. A leaving group, a strong leaving group.
Oh, sweet. Halogen.
Sorry, no.
the most important thing when assessing an SN2.
Oh, primary.
Sterics, so primary, right? So that's one of these tantamount things, right? You guys said, numbers 2 through 11, right, on important things. And you're all right? You guys are right with all that stuff. But don't forget sterics is kind of one of the first selective criteria for it, right? So we have a primary leaving group that's good and a strong nucleophile, SN2, okay? All right. So that's what we make. You can buy that in a bottle. Okay, you can buy it by the kilogram if you want. Nice, stable, organic salt. Okay? These things usually precipitate out of solution, easy to make. Okay? And you can buy it in a variety of different flavors, and we'll talk about why that's important in a little bit. Okay? But the point being this. Triphenylphosphine is nucleophilic, and when you put it under the appropriate conditions, you're going to end up making this ionic compound, okay? Where there's a formal positive charge on the phosphorus, and anytime you have a positive charge, you have to have a negative somewhere. Oftentimes, we just kind of play loose with the rules, and we don't really care about balancing things all that much because we know there's a sodium around or something like that, right? But there always is a charge around. And here it's particularly important, okay? So we have this salt here, okay? Now if I take this salt, and what I'm going to do with it here. Okay, so let's take that exact same thing and draw it one more time because we all need practice. Drawing hexagons. Okay. Okay? Now if I take this and I put it in the presence of a strong base, usually we end up using something called N-butyl lithium, right? Sometimes abbreviated as NBULI, right? N-butyl lithium. Now, you guys already knew that was a strong base. Why?
It's organolithium.
Because it's an organolithium. And whenever you guys see an organolithium, what do you guys see? A really powerful base. You also see a carbon with a lone pair and a negative charge, right? It's hard to get a much stronger base than that. It really is. So, guess what that N-butyl lithium is going to act like? The base. So, it's going to go after the most acidic hydrogen. Okay? Now the most acidic hydrogen happens to be the hydrogen next door to the phosphorus. Okay? You guys with me on this? Do you guys see the hydrogen that's next door to the phosphorus? I should technically say the hydrogen on the carbon next to the phosphorus. Right? So on the alkyl chain, it's going to deprotonate that. Okay, so one of these hydrogens here are going to come off. Okay, so just for argument's sake, remember organolithiums basically look like snakes. Okay? I don't know, that always reminded me of a snake when I was going through this. No, Dr. Mage. That's not what it looks like. It looks like a worm. So for all intents and purposes, we make this. Isn't that unusual? And you guys would say?
No.
Oh, okay, you're like, no, not great, no. I got that in my bottle at home on the shelf. Put a little behind the ears in the morning, I'm good to go, all right? I'll go ahead and answer your question for you. Yeah, Dr. Aries, that's pretty unusual. What's unusual about this? Yeah, we got a negative and a positive on the same molecule, right? And that is actually the stable structure, okay? Now this is what's known as a Zwitter ion, from the German word for two, zwei there, right? So Zwitter ion, Z-W-I-T-T-E-R, Zwitter ion. And that's actually some very common Zwitter ions that are, you can make, okay? Now, if you take a look in the book, they actually, this is one of the, this book has these kind of little subtle things in there that I don't think, well, I'm not going to get into a pedagogical argument. All I was going to say is the book impresses me when it has some of these like little tidbits in there that it mentions, which I think are far more important than it gives it credit for. But anyway, so just to kind of zoom in on what we have there, right? We've got a lone pair and a negative charge there, we've got a plus charge there. Now, what do we know about phosphorus? So, we know it has a lone pair. Okay, got it, right? Right? What else do we know about phosphorus with respect to differences from carbon or nitrogen or oxygen or fluorine? Okay, well let's think here for just a second. What makes carbon, nitrogen, oxygen, and fluorine particularly annoying in some cases? We can't expand the octet, right? They're locked by the octet rule, right? But as soon as we step away from those four, then we can start to violate the octet rule, right? Meaning what? When we have phosphorus, we can make 5 or 6 bonds to it, okay? So a thought, and it wouldn't be a particularly bad thought, is that we could draw some kind of resonance structure wherein we set up some kind of system like this, where we actually see a neutral species, right? Because what happens when you put a negative and a positive together? You make a neutral species, right? So if you're like, well, I don't believe you, Dr. Hayes, we'll go through and do the formal charges on this. You'll see if you have 5 bonds to a nitrogen, you don't have a formal charge on it anymore, right?
Wait, nitrogen?
Phosphorus, excuse me. I mean, the same would be true for nitrogen. Yeah.
Wait, why wouldn't nitrogen be able to do that even though?
Good question. So ask me that question after I'm done yammering about this. It's a good question.
Okay.
So, all logic would say what? Which is the better resonance structure? The one on the right. However, guess which one is actually the better resonance structure? The one on the left, right? I thought, see, isn't this stuff unusual? Like, no, Dr. H, we already told you. Very normal, right? Now, there's a really, and this is what I was talking about, why I appreciate what the book says. So, one thing that we take for granted, or that we might just make a lot of assumptions about, is that when we draw bonds in between things, we just put lines on paper. Not all bonds are of the same strength, right? Now, you guys know that because that's why we say that bromine is a good leaving group, and iodine is an even better leaving group. It's not necessarily just because of the atomic radius, it also has to do with the strength of the carbon-bromine and the carbon-iodine bond. Right? They're weaker because they have a bigger difference in the radius. Now, to draw into that thought here for just a little bit, right, one of the differences on phosphorus and from the other things is that it's a larger atom, right? Now, I forget the name of the theory. Oh, I forget a lot of stuff today. I almost forgot to come teach you guys too, which is always good. No, I got caught up in writing a paper, and it got interesting, and so I'm like, oh crap, I gotta go. Then I forgot my pen, I forgot my adapter, I forgot the Jolly Ranchers. It's Friday, what can I say? All right. Anyway, but one of these things that we forget, and I forget the name of the theory here, is if you have a big mismatch in the size of the atoms. Remember, the size of the atoms is purely related to the size of the orbitals, right? Bigger atoms have bigger orbitals, hence a bigger radius, okay? And if you have a mismatch in the orbitals based off of their size, you actually make weaker bonds. And it just so happens that given the setup of this Zwitter ion there, where you have the plus and the minus together, we can't really form an overlap to make that double bond. Because we're assuming that the p orbital of the carbon can overlap with the p orbital of phosphorus. It just really can't happen. So we really can't make that double bond all that much. Okay? Everybody with me on that? Here's what I'm saying, okay? No do thing right, thing left good, okay? But there is an explanation behind it, and it's actually really important for any of you guys who are going on to graduate school, which is what, 1, 2, 3, 4, 5, 6 of you guys in here, right? So it's a get your PhD for free. Go to grant, go get it, right? I'm going to pay $250,000. Okay, right? So, right? Phosphorus, because of its unique kind of electronic structure, it has trouble, or it has unique bonds that can get formed to it, is all I really want to say. We'll keep it at that. So, bringing it back to the practical aspect, when we're going to use this in the next part of this reaction, okay? Now, let me point out the obvious to you guys again. Why is it important to look at that structure on the left and go, yep, there it is? What's step number one for all of organic chemistry?
Find positive bonds.
Find your positive and negative. Now, why do you guys like Wittigs? Where's the negative? Right? It's right there, right? It's blatantly obvious where the negatives and the positives are with this Wittig reagent, right? So this is, and the other name for this is the ILID, is what it's, right? Isn't that what they talk about? Yeah, they call it that in the book, right? So ILIDE, or Zwitter ion, or sometimes Wittig reagent. That's an annoying noise. Let's talk about me. All right. He just won't shut up. You guys with me on this? So if I ever say ILID or Wittig reagent or Zwitter ion, right, it's all talking about the same thing. Oh, there should be a, forget it, who cares? Okay, right, so that thing on the left. Good?
That noise is really annoying.
Yeah.
Why did you point it out?
Yeah, I didn't notice it.
I didn't
So
notice
you
it.
guys would have noticed it without me. Eventually I do shut up.
I think it's like a vacuum cleaner.
Same. We can go outside.
We'll go yell at him in a minute. Who the hell do you think you are? I'm trying to teach about Zwitter ions, damn it. All right. All right, anyway, so I forget I'm recording. All right, so I'm going to, that's fine. It's more evidence. Okay. All right, so how does a Wittig work? So if we take a ketone or an aldehyde, okay, and if I put my ketone or aldehyde along with my ILID, okay, so the thing that I made in the previous two steps, got it? So what I'll end up making as a product here, okay, so when I'm talking about ILID at this moment, I'm talking about that specific one right there, okay, you guys with me? What I'll end up making is this.
Beautiful.
It is actually.
Do we need to know the mechanism for that?
Yeah, sounds good. Okay. We'll make that one right there. Do you guys see what we did? What did we do? We took a carbon-oxygen double bond and we swapped it for a carbon-carbon double bond. Selectively add ketones and aldehydes. Freaking amazing, okay? Really, really cool stuff. Okay, tell me how it's done. So propose a mechanism for me. I'll give you a hint. Find your negatives and positives. You know where the negatives and positives are in the ILID, right? Do you have negatives and positives on a ketone? I wonder what's going to happen. Now take a look at your product, the other product that gets made. Where does the ketone oxygen end up? On the phosphorus. Got it? too bad. I like that. So negative attacks positive, and negative attacks positive.
So,
Mm-hmm.
does that, does,
Mm-hmm. That actually happens first. Well, sort of first. Because otherwise, what reason would that have to attack that? Remember, these are negative-ish, right?
yep.
So draw what that looks like. Negative attacks positive, which makes that negative, so it's going to attack that. There you go. So draw what that's going to look like. Mm-hmm. Now finish it up. You know what your product at the end has to be, right? You have to make a double bond from here, and you have to make a double bond here, right? Mm-hmm. So draw what that intermediate looks like. Careful. Negative always attacks positive. Where's your big negative again? Negative always attacks positive first, right? Negative is going to attack positive first. Where's that going to attack? So show that happening. Good. So draw what this is going to look like. Okay, so you got negative and positive, right? So this is going to attack there, and then what happens with those two?
I think it's gonna like go around here. Attack.
We'll take a look at the end, right? The oxygen has to get attached to the phosphorus, so at some point this has to meet that, right? But that's what I'm saying. You have negative and positive here, and you have negative and positive there. Right, they're both going to come together.
Is it wrong? Or is it just?
No, you're on the right track. It just looks kind of weird, doesn't it?
Yeah.
No, man, it's almost like you're learning something new.
Stop.
I want everything to be the same, Dr. Reed. You don't understand.
I don't know how much of a creature of habit I am. Like, for real.
So I'm gonna do myself a favor, because I already know what the answer is, so I'm gonna make this a little bit easier on myself. Okay? Why did I draw it like this instead?
It's easier to pay attention.
Yeah, because this is negative and this is positive. So what's gonna happen? Negative attacks positive, right? So watch with me here for just a second. So if we assume this happens first, so the negative attacks the carbonyl carbon, what happens next? This gets popped up, right? Which means that I would have this, right? And then what would happen?
That attacks the phosphorus, like the negative.
Right? You guys with me?
Yeah.
So, but this all happens basically at once. Alright, so you can draw that right there, okay? Okay, so how does that look? Looks stupid, okay. Alright, so there's my carbonyl carbon, which is bound to my oxygen, right? What's my oxygen bound to? Phosphorus right? Phosphorus is bound to carbon, and that carbon is bound to that carbon there. You with me? We've got those two methyl groups there, and then we've got the rest of the shenanigans coming off of that carbon. Good? So I have this four-membered ring intermediate. Four-membered, I said four. Call that a square. Now what? So take a look at my product. in my product, my oxygen has to have a double bond with the phosphorus. Right? Okay, so we make a double bond here. Right? We do that right there. Okay?
Can you say that part one more time?
Yep, 2 arrows.
Yeah. 2 arrows, but
That's it.
girls confused.
Okay, what you confused about?
I don't know why those arrows just don't make sense to me. Can you like state your little spiel again?
Well, I know I have to make the double bond to the oxygen in my, as part of my product, right? Right? So I have to break a bond from the oxygen to make a double bond to the phosphorus, right?
Okay, gotcha. Like you open the door.
Yeah, basically, right? But we go through a subtly different mechanism here, right? We do go through a, what they call a 2+2 cycle of addition. Don't worry about that stuff. You guys with me on this? That's not too bad, right? Is any of this mechanism difficult? No, it doesn't look different. Sure, right? But remember, to make my illid, I do an SN2, followed by an acid base. And then what do I do here? A series of nucleophiles attacking electrophiles, right? Negatives attacking positives. And then I just switch the bonds. Got it? Not too complex. Once you see it once and practice it once and twice, right? Okay, question. Why shouldn't this work? Why does this not make sense immediately? Take a look at my product, what I'm doing. What am I trading in my product? It's one of these important ideas.
Carbon oxygen bonds or carbon-carbon bonds.
Yeah, so what do we know about carbon-oxygen double bonds?
They really love them.
They're stronger than carbon-carbon double bonds. But this reaction proceeds very cleanly, very nicely, very easily, very goodly. Why? What about phosphorus?
It's weird.
What bonds are stronger than carbon-carbon double bonds?
Phosphorus oxygen.
What kind of phosphorus-oxygen bond did we end up making? Aha. So if you think about this, we traded one ketone for a phosphorus-based ketone. You guys with me on this? We traded a carbon-oxygen double bond for a phosphorus-oxygen double bond. Phosphorus loves oxygen. Phosphorus loves oxygen. So we traded a strong bond for a stronger bond, is what it is. Now, not to get too morose or too into the weeds here, but the idea that phosphorus loves oxygen is actually important in certain ways, I should say. Right? You guys ever heard of Dresden? The city of Dresden, Germany?
Yeah.
A firebomb during the war? What did they drop on it? Phosphorus, right? So when phosphorus finds oxygen, it will burn, and it's extremely exothermic, and it's a very fast reaction to happen, right? So chemical warfare, right? This kind of idea here, right? Phosphorus is important for a lot of incendiaries, okay? So phosphorus and oxygen, good buddies, right? So better buddies than carbon and oxygen in some ways. Okay? So why is this important? I can selectively link together carbons where a carbonyl used to be. And not only that, but what do I leave behind? I leave behind a carbon-carbon double bond. Can you guys, that's a functional group that you guys know how to do a lot of chemistry with, right? You guys with me on this? If we just link them together and then we have to, there's no functional group there, then that's kind of the end of the synthesis, right? But now we have a double bond, which you guys could add a halogen to, or we could oxidize it, or we could cleave it apart, whatever, right? There's a bunch of different things we can do with it. Good? The all complete understanding. All right. Yes. We understand. Okay, let's see if we understand. I'm thinking of something tricky you guys been thinking of. Okay, so do this. Draw you guys out of your deep contemplation, but Taylor asked a good question. Okay? Your question before all this was, why can't we do this with nitrogen? Right? Yeah, it's a good question. In theory, you guys could do this exact same thing with nitrogen, right? But there's an important difference between nitrogen and phosphorus. What is it? The radius. Okay. So if you take a look, radius is the key as to why we can do this the Wittig reaction. We have to have a larger molecule, okay, that can fit all these bonds around it, okay? Especially when we make that intermediate there, right? So it's all dealing with radius. You can't do this with nitrogen. It's too small of an atom.
In theory, let's say carbon was a bigger atom, we would technically be able to make more bonds than before.
Exactly, yeah. Yeah, there's nothing, electronically, there's nothing preventing carbon and nitrogen from having more than 4 bonds to it,
Yeah.
right? it really comes more down to the sterics of fitting all this stuff around there. I mean, I'm simplifying that quite a bit, but in essence, that's probably a very good medium. Right? Although they did, a couple years ago now at this point, they actually did release the first crystal structure of carbon with 6 bonds to it. So, you guys see, I've been taking points off your guys' exams for all these wrong answers. When you guys put more than 4 bonds to carbon.
So you're telling me my 5-bonded carbon was actually fine?
No, I'm telling you that was 100% wrong. You will notice I said they released a structure, the first structure ever, with 6 bonds to it. So, you did not invent new chemistry.
Does carbon with more bonds have like any, like, decline in our health, like if you like come in contact with it, or?
You'll never come in contact with it. It's way too reactive. Right? I mean, unless somebody like walks up to you with a needle and injects it into you. Literally there's no other way. As soon as this stuff kind of hits air, it'll decompose, either violently or not, right? But yeah. Yeah, but it's not a true bond. Most of these bonds are what they call 3-center 2-electron bonds. So we have 2 electrons kind of bonding in between 3 atoms, rather than 4 electrons like you would expect. Right? So it's a bond by technicality, sort of. All right. All right, so there's some thoughts for you guys. Let's call it some homework for you guys to ponder upon. Good practice for you guys to maybe remember reagents that you might see on quizzes that magically show up at certain times. Right? Might be part of reviewing for exams that show up. So I'll post a message about what sections are on the upcoming exam. I mean, you guys already know the answer. What's on every exam?
Everything.
There you go, right? So why do I have to keep doing this? Just huh? Yeah.
Now we know what we're doing.
Sorry, it's everything except chapter 32. Because there's no chapter 32. Okay. Sounds good? All right, we'll call it an early-ish day from there, right?
I just
Gonna get that